This talk is still on deserialization. We have Quan Chang from Tsinghua University. All the others are from the same institution, and the talk is Automatic Policy Synthesis and Enforcement for Protecting Untrusted Deserialization. Let's welcome our speaker.
Thanks for the great introduction. I'm Quan Chang. Hello everyone, I'm Quan Chang from Tsinghua University. Today I will be presenting on automatic policy synthesis and enforcement for protecting untrusted deserialization. Oh, this one. Okay. Serialization and deserialization are essential mechanisms that transform objects into bytestream and back. These mechanisms allow developers to seamlessly transmit objects through networks or store them into database or files. However, this mechanism poses a significant risk called deserialization attack. During attack, attackers can craft a gadget chain that serialize it into bytestream. If the application deserializes the bytestream from attackers, it can cause serious consequences like RCE. The gadget chain is a carefully designed object with special structures. When the application deserializes this object, it will invoke a serious methods as the attacker intended. For example, this gadget chain will guess the application to construct a runtime object and invoke its execute method, resulting in RCE attack. The primary method to defend against deserialization attack is to validate the type of objects being deserialized according to a policy, thereby blocking the deserialization of gadget chains. To support such defense strategy, the community has already provided flexible mechanisms that allow developers to establish customized policy for their projects. For instance, in 2014, Xdream introduced a security framework designed to facilitate policy enforcement. In 2016, JAB 290 introduced the object input filter to secure deserialization with a customized policy. Moreover, FedJSON has integrated an internal block list since 2016. These mechanisms enable developers to use block lists and allowlist to mitigate deserialization attack. Despite these measures, deserialization attacks remain a serious threat because creating effective policy is still a difficult task. Let's consider a motivation example. This code serves as a patch for serious deserialization vulnerabilities from the Outphase project. From the beginning, Outphase directly exposed an deserialization entry without any defense, leading to the first CVE. To mitigate this vulnerability, the developers first customized an allowlist according to Outphase requirements, as shown left. Such an allowlist can effectively prevent malicious deserialization. However, for convenience, the Outphase developers permitted the deserialization of all JDK internal classes whose name starting with Java. Attackers soon discovered that this allowlist was not strict enough, allowing them to utilize java.ami.server to perform AMI attack. Therefore, the second CVE was exposed and addressed with a block list, which rejects classes with name containing java.ami.server. However, formulating a block list solely based on known gadget chain is not sufficiently secure. Soon, attackers discover other exploitable gadget chains, causing the third CVE. After fixing these vulnerabilities, the policy was eventually strict enough. Nevertheless, vulnerability can also stem from improper implementation of policy enforcement, as evidenced by the first CVE. Specifically, the issue lies in the allowlist regular expression matching, which can be bypassed by attackers to deserialize arbitrary classes. So the process of fixing these CVEs we demonstrate two challenges of protecting Java application from deserialization attacks. First, formulating allowlist policies requires significant effort and is prone to error. Second, enforcing this policy across various deserialization libraries introduce complexity and an increased risk of mistakes. Therefore, we propose DeseriGuard, a tool designed to automatically synthesize and enforce allowlist policies for Java applications. DeseriGuard contains two components, which are responsible for policy synthesis and policy enforcement, respectively. During policy synthesis, DeseriGuard construct a semantic-aware property tree based on application source code and synthesizes the policy. Then it performs runtime instrumentation on application source code, a bytecode with the Java agent to enforce the policy. During the policy synthesis, DeseriGuard first builds a sept from each deserialization entry based on application source code. Nodes of sept are Java classes, which are connected with the property edges and the inference edges. Sept captures all potential structure of the deserialized object, from which we could find all necessary classes for deserialization entry. The construction of sept starts with identifying its root node, which is the class returned by the deserialization entry. As the source code shows, the read object method returns the object class. Hence, the root node N0 of sept is the object class. Please note that for each deserialization entry, DeseriGuard will build a sept and formulate a policy. Since the deserialization entry methods of libraries since the deserialization entry methods of libraries are limited, DeseriGuard can identify root nodes by locating these methods invocations. The root nodes N0 object class, which is a common ancestor of many exploit classes on gadget chains. Classes like object, serializable, and comparable are considered as general classes. Including these general classes in the allowlist will also permit the deserialization of many exploitable classes. Therefore, DeseriGuard analyzes the data flow to identify specific classes that this general class will be cast to. For instance, DeseriGuard traces the data flow from the deserialization entry to determine the object's usage. It discovers that the object is cast to either the profile or session class for application's functionality. Thus, the nodes of profile and session are connected after the node 0. Once a class is added to sept, DeseriGuard first analyzes its properties to construct property edges. A property edge connects a node to the classes of its properties. In detail, the session class has 4 properties of different classes, and thus 4 nodes, labeled from N3 to N6, are connected to the node of session. Subsequently, DeseriGuard recursively analyzes 4 new nodes. For the node N5 of time class, it has no child classes, and its property consists only of basic types. Thus, DeseriGuard terminates the analysis on this subtree. These basic types include the string class and the Java's primitive types. Besides property edges, DeseriGuard needs to construct inference edges to record the complex inheritance relationships among classes. For example, the user class has 2 subclasses, admin and guests, and these 2 classes are connected to the node user with inference edges. However, for general classes, we shouldn't automatically add all their subclasses as child nodes. Instead, we conduct a data flow analysis to more precisely determine which classes the properties will be cast to. After establishing both priority and inference edges for all nodes on sept, DeseriGuard completes the construction of sept. Then we can create the allowlist by including all classes on sept. With the policies, DeseriGuard then automatically enforces them on different deserialization libraries. Specifically, by using Java agent, DeseriGuard performs runtime instrumentation to insert activators and auditors into the application's bytecode. An activator is instrumented before and after each deserialization entry to specify corresponding policy for that entry. Please note that DeseriGuard chooses to protect all deserialization entries of a project because it is challenging to determine whether a deserialization entry is exposed and exploitable. As for the auditor, it should validate the object type after the deserialization libraries identify the class using their resolving methods. Since distinct libraries have very different resolving methods, DeseriGuard needs to automatically locate the invocation position of resolving methods. It first performs a dataflow analysis to locate the potential invocation positions. Specifically, it detects the data flow pattern that goes from a byte stream and then to a class of object and finally back to the constructed object. Then DeseriGuard performs a runtime validation to find the correct position from these candidates. With activator and auditor instrumented at the proper positions, DeseriGuard can validate each deserialization operation in real time. We evaluate DeseriGuard from two aspects. We evaluate DeseriGuard from two aspects. First, we evaluate DeseriGuard on 12 critical real-world vulnerabilities. Then we compare DeseriGuard's policy with 109 developer design policies. These developer design policies are collected from 40 projects, which all gain more than 100 stars on GitHub. To mitigate real-world vulnerabilities, DeseriGuard analyzes projects on average comprise 1.11 million lines of code. This project includes around 20.68 thousands of classes, among which there are numerous exploitable gadget chains presenting a significant challenge for analyze. On those projects, DeseriGuard achieves a 100% defense rate without triggering any false alarm. According to the functionality of different vulnerable deserialization entries, DeseriGuard synthesizes policies with 1 to 623 rules, permitting the deserialization of 1,342 classes. The most complex policy is the synthesis for the outfits, where developers decide a map containing diverse objects. When compared to the total number of classes across projects, DeseriGuard's policies permit at most only 0.0481% of total classes. Next, we display the comparison rate of policies from DeseriGuard and those designed by developers. The comparison rate is indicates the proportion of permitted class to the total number of classes. The median comparison rate of DeseriGuard's policy stands at 0.04%, while that of developer design policies is 19.02%. It demonstrates that DeseriGuard offers a more effective defense by enforcing a stricter policy. When observing the difference between DeseriGuard's policy and the developers' policies, we found that DeseriGuard permits 99.12% fewer classes. However, as shown by orange bar, DeseriGuard may allow 1 to 85 additional classes that are not included by developers' policies. It is because DeseriGuard should over-approximate all necessary classes, inadvertently including some unnecessary classes. Nevertheless, attackers are unlikely to find exploitable guiding chains from these additional classes. Thank you for listening. Feel free to ask any questions.
Let's thank the speaker. Questions?
Hi, Roland Yap from NUS. Okay, so if you look, I can see that you have log4j in your evaluation.
Yes.
Right?
Yes.
And log4j, eventually, they just remove deserialization.
Excuse me?
So in log4j, right, essentially what they did in the end was to remove deserialization. They just removed the feature of deserialization. You can always remove it.
This log4j, this vulnerability is not that log4j is not the recently exposed vulnerability of log4j, and it's a old version log4j that utilizes the deserialization mechanism to deserialize some event.
Right. But if you look at the famous log4j one, right, is the deserialization vulnerability.
The famous log4j vulnerability is not caused by deserialization. It's a GNDI attack.
Yes, but there's a deserialization. You can use deserialization there in the GNDI attack, right? And anyway, the point of the question is that it's not clear to me whether a policy will be necessarily safe. Because in order for a policy to be safe, you have to show that it is safe.
Sorry?
In order for a policy to be safe, you have to show that this policy is safe. For example, provide a guarantee that the policy is safe.
How to guarantee you mean how to guarantee the policy is safe?
Yeah, that the policy has no attack possible.
First, yes, we have no way to validate whether the sensitive policy is safe, but compared to the original code that exposed the deserialization entry directly, which may permitting the deserialization of any classes. We restrict the deserialization, or we restrict the policy and allow only about 0.04 classes to be deserialized. So we have
right. But that's just saying that there'll be less classes deserialized.
Yes.
That does not mean that it is safe. That's all.
I know that. One more. Yes, it is.
Can we say maybe that the attack surface is significantly reduced? At least.
So the lesson from CFI is that many CFI papers, they compare, how many less control flows you can have.
Yeah.
But actually the attacker doesn't care. Attacker only needs one.
One, yes. So that's a deep question that, there's plenty of research, follow-up research to conduct on that.
And there's some CFI papers which discuss that this metric is wrong.
Yeah. No, thanks. That was a good question. I have a short one, and then we let everyone go to a break. Unless there are questions, we have 1 minute. You have more questions in the audience? Sorry, I was eager to ask my own question. I'm curious, you mentioned 109 developer design policies. Can you tell us how did you find them? Like you mentioned GitHub and stars, but I wanted to know how you scraped them in the code, how you found these developer design policies.
First we search this project from the GitHub and by searching with some keywords that developer usually use to enforce policies. For example, developers may use object input filter to set policy for Java, or to use add permission, extreme dot add permission to set policies for extreme libraries. So we use this keyword to search, and then we pay extensive attention to validate this project and collecting the policies.
Okay, so keyword and then manual filtering. Thank you very much. Let's thank the speaker once again.